Relief device selection, general criteria. Relief device selection must ensure both mechanical integrity and operational compatibility with the process conditions. Each relief valve must have manufacturer-verified data confirming it is suitable for the specific service, including fluid phase, pressure, temperature, and flow characteristics. Standardization approach. For consistent application and ease of maintenance, relief valves should be selected from a standard range of sizes based on API 526 up to orifice designation 8T10. Each orifice size corresponds to a specific inlet-outlet configuration and orifice area. 1D2, orifice area 0.71 centimeter, orifice area 1.26 centimeter, 1/2 F2, orifice area 1.988 centimeters, 2H3, orifice area 5.06 centimeters, 3K4, orifice area 11.86 centimeters for out of 6, orifice area 18.41 centimeter, 4P6, orifice area 41.16 centimeters, 6Q8, orifice area 71.23 centimeters squared, 6R10, orifice area 103.233 centimeters squared, 8T10, orifice area 167.75 centimeter. Additional selection guidelines for services requiring larger capacities than 8T10 pilot-operated relief valves may be used, but only if the process medium is clean and dry. Relief valves must be adequately supported to handle the dynamic reaction forces during flow events. The minimum flange rating should be inlet SME class 300, outlet SME class 150s. Flanges must be integrally cast or forged with the valve body. Flange surface finish must match the piping class to which the valve is connected. Relief valves in steam service that discharge to atmosphere should be of the exposed spring type hit if operating above 250 degrees Celsius. Manual lifting devices are permitted only for steam, hot water, or air service. Test rods must not be used, as they may inhibit stem movement and are sometimes misused to block the valve during transport or hydro testing. Where multiple valves operate in parallel, say set pressure staggering, should be used to avoid simultaneous lifting and potential valve chatter. The valve configuration must also accommodate easy maintenance access, safe discharge routing, and robust performance under transient or emergency conditions. Relief device selection, specific criteria. While spring-loaded relief valves are the most common type used in process facilities, specific process conditions may call for alternative designs. The correct selection of relief device type must account for back pressure, service cleanliness, sealing reliability, phase behavior, and response requirements. The following outlines the criteria for selecting various types of relief devices. 1. Non-balanced spring-loaded relief valves used when built-up back pressure does not exceed the maximum allowable overpressure. Suitable where back pressure is low and relatively stable. For constant back pressure, e.g., downstream pressure that is always present, the spring should be selected to account for this offset from the set pressure. If discharging to a closed system, a closed bonnet must be used to prevent process fluid release. Limitations: not suitable if total back pressure, including simultaneous valve discharge, risks raising actual valve opening pressure above equipment limits. May require lower set pressures in systems with variable back pressure due to shared headers. Balanced spring-loaded relief valves, bellows type, required when built-up back pressure exceeds that tolerated by non-balanced valves, can handle back pressure up to 50% of the set pressure. Must be fitted with a vented bonnet to atmosphere or a safe location. Bellows material must resist process corrosion, otherwise consider a balancing piston as an alternative. Avoid bellows-type valves in freezing or icing services. Moisture ingress can freeze in the bonnet and impair valve function. Not suitable for dirty or fouling services where bellows can be damaged or blocked. 3. Pilot-operated relief valves. Recommended in clean, dry services where reliable pilot operation can be assured. Use non-flowing pilot types to avoid drawing contaminants into fine internal passages. Applicable when inlet pressure drop exceeds 3% of set pressure. Tight shutoff is needed. Soft-seated pilots offer excellent sealing. High back pressure exists, greater tolerance than spring-loaded valves. Large capacity or high-pressure service makes spring-loaded valves impractical. The margin between maximum operating pressure and set pressure is 10%. Must avoid blockages due to hydrates, wax, or solids, eliminate low points in sensing lines, provide heat tracing and insulation where necessary. Filters must not be used in sensing lines due to blockage risk. Provide field-accessible devices to verify set pressure. 4. Air-assisted relief valves. Non-balanced spring-loaded valves with a pneumatic actuator. Allows for reduced margin between operating pressure and set pressure, as low as 5%. 3 actuation strategies. 1. Opening assistance only. Spring set to 105% of design pressure. Actuator ensures opening at set point. 2. Closure assistance. Spring set at 100% of design pressure. Actuator maintains seal close to set pressure. 3. Combined action. Spring at 100%. Actuator both holds shut and assists opening. Ensures relief within 110% of set pressure even if actuator fails. Must be designed to fail open or fail safe under instrument malfunction. May not be recognized under certain pressure vessel codes. Use may require regulatory approval. Follow IPF level design rigor when applying air-assisted valves, including logic voting, diagnostics, and reliability assessment. NAR 5. Bursting discs should generally be avoided unless justified by application needs. Not reusable, must be replaced after rupture. Advantages: fast response time, e.g. for exchanger tube rupture or sudden gas breakthrough. Suitable for vacuum service to prevent backflow. Can protect a relief valve from corrosive or solidifying fluids. Leak-tight barrier for toxic fluids. Cautions: use J reverse buckling type for durability and reliability. Discs may pinhole or fatigue, causing pressure equalization and preventing rupture. Must vent the space between the disc and relief valve to avoid pressure buildup. Install pressure gauge or alarm between the disc and valve to detect rupture. Do not install 2 discs in series to avoid issues with fatigue and creep. Apply generous margin between bursting pressure and operating pressure. Tension-loaded discs 30% above MOP. Reverse buckling discs get 10% above minimum burst pressure. Take into account the temperature effect on bursting pressure. If a disc is installed upstream of a relief valve, apply a derating factor of 0.9 to valve sizing unless flow testing justifies a different value. Correct selection and application of relief devices ensure dependable protection of process equipment during overpressure events. Each type offers unique benefits and limitations and must be matched to the specific pressure profile, media characteristics, and system configuration of the process being protected. Relief device design considerations. Relief devices must be sized and configured to handle the most severe individual overpressure scenario applicable to the equipment. This ensures the protected system remains within its allowable stress and pressure limits under both fire and non-fire conditions. Set pressure and accumulated pressure limits. The relationship between the set pressure SP, design pressure DP, and maximum allowable accumulated pressure depends on the type of relief scenario, fire or non-fire, and the number of valves installed. The following limits apply. Single relief valve. Set pressure 100% of design pressure. Maximum accumulated pressure. Non-fire case 110% of DP. Fire case 121% of DP. Multiple relief valves, at least one valve set at 100% of DP. Other valves may be set up to 105% of DP, maximum accumulated pressure, non-fire case, 116% of DP, fire case, 121% of DP. Notes: relief valves for fire service may be set at 110% of DP only if separate protection exists for non-fire cases. For set pressures below 10 bar, staggering pressures becomes impractical due to limited tolerance margins. TASH. Overpressure calculation parameters. Overpressure used for valve sizing equals maximum allowable accumulated pressure minus set pressure. Inlet piping pressure drop must be 3% of set pressure. Design tip. Increasing the design pressure beyond normal operating needs can reduce relief valve size and discharge piping, especially when wall thickness is driven by factors like wind, vacuum, or mechanical loads, not internal pressure. Blowdown pressure. The reseating pressure blowdown must be higher than the maximum operating pressure to avoid repeated valve cycling. Blowdown is typically 5 to 7% below the set pressure. If set too close, valve chatter and damage can occur. Operating margin. A sufficient margin must exist between set pressure and maximum operating pressure as defined in project or industry-specific design guidelines. This avoids nuisance lifting and extends valve life. Material selection and temperature limits. Valve materials must be compatible with the fluid properties, e.g. corrosiveness, fouling, the extreme temperatures expected during normal and emergency scenarios. Springs must withstand all non-fire temperature extremes. Spring coatings. Cadmium and zinc coatings are prohibited due to risk of embrittlement. Aluminum-based coatings are acceptable. For services not listed in standard references, materials must be selected based on fluid properties and verified with the design authority. Correct application of these design criteria ensures that pressure relief devices not only protect against overpressure events, but also operate reliably and repeatedly over the life cycle of the equipment. Relief device sizing methods. Proper sizing of relief devices is essential to ensure they perform effectively under emergency conditions without excessive cost, noise, or mechanical stress. The sizing methodology depends on the relieving phase, gas, liquid, or two-phase, and the process scenario being addressed. Establishing relief scenarios. Each relief valve must be sized based on the most severe applicable relief condition, typically determined through scenario evaluation, e.g., blocked outlet, fire exposure, control valve failure. All assumptions, design basis conditions, and calculations should be documented using standardized relief valve sizing sheets. For each valve, the largest expected relief load is used to determine the required orifice area and associated inlet-outlet piping dimensions. 2. Sizing for liquid relief. When relieving liquid only, use the certified valve method from industry standards, e.g. API. This method provides more accurate sizing, helping to avoid oversized valves, which can lead chatter, rapid cycling, premature wear, loss of sealing integrity. Ahers 3. Sizing for two-phase flashing flow. Standard gas plus liquid sizing methods, e.g. summing separate gas and liquid flows, are not valid for flashing or two-phase conditions. Two-phase fluids choke at lower velocities than single-phase gas but behave differently from liquid. This makes conventional gas-liquid calculations non-conservative. Use the homogeneous equilibrium model, which assumes no slip between phases, gas and liquid move at the same velocity, instantaneous thermal equilibrium between phases. This model provides a physically accurate and conservative estimate of two-phase relief area requirements. Proper two-phase sizing requires iterative flashing calculations across a range of downstream pressures to identify the critical choked mass flux. 4. Computational tools and support. Relief sizing for complex fluids or two-phase conditions should be supported by thermodynamic models or simulation software that can accurately calculate fluid properties, enthalpy, density, specific volume, model successive pressure drops and phase changes. Calculated relief areas must be adjusted using a coefficient of discharge, KD, to account for valve performance under certification standards. Hashraf 5. Key objectives in sizing. Ensure the orifice is large enough to relieve pressure under the worst-case scenario. Avoid oversizing, which can cause valve instability, excessive cost, unnecessary loads on downstream piping. Confirm inlet and outlet piping are sized to handle the relief flow without excessive pressure drop, especially important for preventing valve chatter. Through scenario-driven, phase-appropriate sizing methods and conservative modeling of complex flow conditions, relief systems can be designed to perform reliably and safely across a wide range of potential process upsets. Relief valve location and arrangement. The physical location and mechanical arrangement of relief valves are critical to ensure effective overpressure protection, minimize pressure drop, and facilitate safe maintenance. Incorrect placement can lead to delayed valve response, accumulation of condensates, and increased risk of malfunction. 1. Valve location guidelines. Relief valves should be installed as close as possible to the protected equipment or system, and ideally at the highest pressure point, often the upstream end. For vessels, the valve should connect to the vapor space above the liquid level or to a vapor line leading directly from that space. If a demister pad is installed in the vessel, the relief connection must be upstream of the demister, unless the relief flow rate is high enough to bypass the pad's influence. Inlet piping requirements. The pressure drop between the protected equipment and the relief valve must not exceed 3% of the valve's set pressure under full relieving conditions. Inlet piping should have no pockets or low points where liquids can accumulate. Piping and valve orientation must ensure free draining toward the vessel and prevent trapping of condensates, solids, or ice. 3. Installation orientation. Relief valves must be installed in the upright position. This applies to spring-loaded valves, pilot-operated valves, air-assisted valves, thermal expansion relief valves. For TURVs, mounting close to the equipment is preferred, even if this creates a pocket provided that the discharge line is protected from freezing or plugging. 4. Atmospheric discharge considerations. Relief valves discharging to atmosphere should be located at the highest practical elevation. 2. Minimize discharge pipe length, enhance dispersion of released gas. These discharge lines must include a drain hole, e.g. 8 mm diameter at the lowest point to prevent rainwater or condensation buildup. 5. Closed system discharge considerations. When relief valves discharge to a closed flare or header system, the valve must be installed above the header to prevent backflow of condensate or process fluids. Relief outlet lines should connect to the top of the header or in such a way that even if the header is full, it cannot drain backward into the relief line. If elevation constraints prevent this, a local drain vessel must be installed. The drain line must be locked open and properly sized, 50 millimeters for headers up to 200 millimeters, 100 millimeters for headers up to 400 millimeters, 150 millimeters for headers above 400 millimeters. The drain vessel should include a high-level alarm set as low as possible to maximize retention time. 6. Heat tracing and insulation. If the fluid has a high pour point or can solidify, apply insulation and/or heat tracing to the inlet and outlet piping. In some cases, flushing the line with a compatible hot process fluid may be used to keep the relief path clear. This often requires a knockout drum downstream to separate liquid from gas before entering the flare. Multiple relief valves and isolation strategy. Systems requiring high availability or in situ testing often include multiple relief valves, e.g., duty plus spare. In such cases, each valve must have inlet and outlet isolation valves, plus appropriate locking mechanisms to prevent inadvertent isolation of all valves simultaneously. Key-operated lock systems are mandatory for block valves on critical relief paths. A vent connection should be installed between the inlet block valve and the relief valve to confirm valve positioning during changeover or maintenance. 8. Thermal expansion relief valves. T-IRVs in piping may require upstream and downstream isolation if they are to be removed while the system is live. Isolation valves on T-IRVs can be sealed open instead of locked, depending on site procedures and risk tolerance. Operator procedures must ensure that blocked-in lines are not left unprotected if the TIRV is taken offline. Correct location and arrangement of relief valves ensure that protective devices operate promptly and reliably under all conditions, while allowing for safe maintenance, testing, and system isolation without compromising process safety.